per protein, which relieves the inhibition of per, it starts producing protein all over again. So it cycles those. Now, how the production of this clock then, what is downstream of the clock, it's not as well known. You know how that's. Obviously, we need something downstream to change the cell, probably the cell excitability or something, so that the fire's action potential is right, or something like this. And that's not as well understood. So in humans, it's been typical to use EEGs to study sleep. Electroencephalogram. And this involves putting electrodes on your scalp and recording the brain activity. It's generally considered a rather crude measure of brain activity, as you can expect. But interestingly, it has been a good method for looking at the various stages of sleep. So basically what you're doing with EEG is you have your scalp, and then you have neurons that are, presumably receiving synaptic input or firing action potentials. And so while they're active, you have some inward current, right, going into those cells. And you have some resistance in the extracellular space. So a current flowing in this direction, going into the cell, is going to set up a extracellular potential, which would then be positive here and negative here. Okay? As that positive current is flowing into the cell. Now, if you have a lot of cells, so this is going to be a very small potential. If you were to look at single cell, the extracellular electrical signal produced by a single cell, you're talking about something that's at the most just a few microvolts, a few thousands of millivolts. I'm getting to the point where it's hard to measure. Now, this is under optimal conditions when you have electrodes that would be stuck through the scalp. You can imagine that even less current is probably flowing along the scalp. And that's where you're making your measurements, right, along the scalp. So the signals from just a few neurons are going to be so small at the scalp that you're going to not be able to measure them with any sort of electrode. What you need in order to get a signal here is you need many neurons firing together. So you would have all of these potentials that would then add up. And so when you're looking at these electromonograms, the more cells you have firing together, the larger amplitude of these waves of activity that you're recording. So when you're recording these cycles, if the amplitude gets large, it means that a lot of cells are synchronized and are firing together. Okay. Of course, the frequency of these waves tells you how frequently the cells are firing. Right? So during sleep, in the awake state, not a lot of synchrony. As you go through these various stages of sleep, you tend to get more and more synchrony, so that in stage 4, which is the deepest sleep, you have high synchrony, you have these large fluctuations in potential. You then progress from stage 4 eventually into something you've all heard of, I'm sure, REM sleep, rapid eye movement sleep. It's called REM sleep because your eyes are moving during this period. So again, REM sleep has some age dependence. It's longer at birth, at least 8 hours. At age 20, your book says it's about 2 hours, and then when you get elderly, it's just less than an hour, about 45 minutes. The interesting thing about REM sleep is that your blood pressure, heart rate, and metabolic rate are actually similar to the awake state. And you can actually see that the brain wave is actually very similar to the awake state. So there's a lot going on in your brain apparently during REM sleep. REM sleep is found in all mammals. During REM sleep, you have a greater prevalence of dreaming. And during REM sleep, there's a paralysis of large muscles. Presumably this keeps you from acting out your dreams in any sort of gross way. Some of the small muscles are not paralyzed, so you get twitching of some of the small muscles, such as the fingers and the toes, and the eye muscles. So you get the movements. There are some pathways that have been identified which are responsible for the paralysis. There are actually outputs that go all the way down to the spinal cord, and actually synapse have an inventory input, the motor neurons in your spinal cord shutting them off. So presumably you can't act out your dreams or whatever during REM sleep, during your paralysis. There also is some inhibition of sensory input, so you have less sensation during REM sleep. Presumably it would be a little harder waking up. Okay, so what's responsible for keeping us awake or making us sleep? And this is still an open question. Although there is some evidence that, in fact, there's a lot of evidence that the reticular activating system is very important for our wakeful state. And there's some studies in the cats that show that if you stimulate this region, you can cause the animal to go from the sleep state to the wake state. So presumably this system, which is fairly far-reaching in the brain, is responsible for keeping you awake and making you alert. There's also some evidence that stimulating in the thalamus can actually produce sleep. Okay, when you're awake, one definition of being awake is that you're conscious. And what is consciousness? Big question. 20 years ago, probably, no one ever asked these questions, and no neuroscientist would ever ask this question, what is consciousness? And the problem being that consciousness is a subjective thing, and so it's hard to study objectively, and so it was just totally off limits. There are people now who talk, neuroscientists, who talk about consciousness and who actually say that they study it. And this may have kind of started with Francis Crick, the DNA guy, who really started talking seriously about consciousness about 20 years ago and started writing things about consciousness and how we should study consciousness. So there are people out there that are thinking about these things, and I just want to finish up with one of the better people who